Good afternoon, everyone. So David Hyde, I lead our alternative propulsion work at the World Economic Forum. And I think if there are two really key messages that people have taken away so far from today, the first is that SAF is going to be incredibly important and vital to the transition, especially in the short term. But the second piece is that it's not the only option on the table. There's a big pressure from both within the industry and amongst society to look at options that completely remove carbon from the equation when it comes to flying. And in turn, we have industry players, be they the incumbents, be they new entrants looking to disrupt the market, who are looking to address that demand for zero emissions flight. But if we are to realize the potential that these technologies offer, partnerships and collaboration on an unprecedented scale are going to be needed. My colleague Laia was up here earlier talking about the work the Forum has been doing with our Clean Skies for Tomorrow coalition, looking at how we can boost the demand and uptake of SAF. The Forum has also responded to this new interest in alternative propulsion by recently launching our Target True Zero project. With this project, we are looking to mobilize the key stakeholders who can make alternative propulsion a reality. That includes players both within the industry, governments, and adjacent industries who are going to be crucial for making this happen. There are a lot of things that we don't know about alternative propulsion now. Some of those are things about what are the capabilities of these aircraft. We also don't really understand what the full-scale environmental impacts will be. It's not enough to just look at what's coming out of the plane, but we also need to look at what's going into the energy generation, the fuel production, and other factors that will determine ultimately how sustainable these technologies are. And we also don't understand what impact this could have on the industry, how it could change operations, how airlines operate. Those are all things that we want to address within our Target True Zero project to begin to have a better idea about to what extent, when, and what is needed to make these technologies a reality. Crucially, what we also want to do is identify the steps that different partners, different stakeholders, and different groups can play to accelerate the development and deployment of these technologies within the aviation sector. Our next two panels today are going to touch on some of those issues. Later on this afternoon, I'll be leading a discussion with some of the new entrants in this space, looking at how we get these promising new technologies to a scale where they can really make a significant dent in the aviation climate impacts. But before that, we'll also be hearing from what is the incumbent industry, so the big three airframers and the big three engine manufacturers. And to lead that discussion, I'd like to invite Robin Riedel on the stage. So Robin is a partner with McKinsey, and he's also a fellow within the World Economic Forum, supporting our Target True Zero project.
Thank you.
Thank you. Thank you.
Thank you, David. I'm super thrilled for this discussion. I'm going to ask our panelists to join us because I think this is the first time, at least that I can think of, that we're going to have the three big OEMs of aircraft and the three big engine manufacturers on one panel to talk about, novel propulsion. So I'm very much looking forward to this discussion. So thank you for joining us. Quickly to introduce the round we have here, Mark Bentel, he's a VP of Advanced Technologies at Airbus. Rodrigo Silva de Souza is the VP of Marketing Commercial Aerospace for Embraer. Chris Lawrence is the Chief Engineer and General Manager at GE. Ryan Yutko is the VP and Chief Engineer for Sustainability and Advanced Technologies or Advanced Mobility at Boeing. Grazia Vittadini is the Chief Technology Officer at Rolls-Royce. And of course, Frank Preli is with Pratt Whitney and leads technology there. So thank you so much for joining us. So as we kind of get kicked off, I would just love to have each of you kind of walk us a little bit through how does your individual company think about novel propulsion in aviation and getting us started down that way. So maybe, Grazia, we'll start with you.
Of course, with pleasure. Thank you. So at Rolls-Royce, our endeavors in the field articulate on three pillars. We have electric and hybrid electric flight. You've all certainly seen the world-breaking flight of our iconic Spirit of Innovation, wonderful aircraft. No, it will not be sold. We're getting a lot of requests, but sorry, it was just a demonstrator and really very indicative of the pace of acceleration when it comes to electric technologies. We're not only demonstrating, we're also pushing for entry into service of propulsive solution with our customers, Vertical, VX4. We proudly partner and strategically partner with Embraer on the EVE spin-out, urban air mobility spin-out. Tecnam and Widerøe on the commuter segment, also all electric, entry into service in the next 5 years. Plus, of course, a lot on the hybrid segment. We've been flying with our P2010 H3PS demonstrator earlier on this year, and have also demonstrated 1 megawatt capability on our test bed. So we'll keep on investing on that specific segment. We don't forget our core. Our core is gas turbines, right? So continuously improving the efficiency with step changes in technology to make our gas turbines more efficient, with the portfolio of technologies on the UltraFan demonstrator, minus 25% fuel burn, minus 40% NOx emissions, minus 35% noise emissions. So this is a fundamental, of course, element of our strategy. Couple that with SAF, 100% sustainable aviation fuel use, you unlock great potential we need to continue harnessing on. Last but not least, hydrogen. Of course, we're exploring the potential and the promise of hydrogen, both in terms of direct combustion and in terms of seeing it as part of an electric circuit with fuel cells and electrical power. So a lot going on at Rolls-Royce, definitely.
Very much sounds like that. Thank you for that overview. I mean, Frank, what's Pratt Whitney doing about novel propulsion? How are you thinking about it?
It might be a somewhat similar answer, but in the core technologies, it's larger fans, higher bypass ratios, and lower fan pressure ratios for more propulsive efficiency. In the core, it's even smaller cores than we have today on our geared turbofan with higher thermal efficiency. So that's sort of the evolutionary progress through high temperature materials and other things that we expect to see. Then electrification. In the small engines, maybe 50% hybrid electrification, as you've seen in the program we're doing with the government of Canada, de Havilland, the government of Quebec. And so that will be demonstrated on the ground this year, and hopefully within a year or two in the air. And so that's a 50% hybrid. That same technology then, and many of the same components can be used in a narrow body application to get significant improvements, but with less of a hybridization component. Then, of course, hydrogen. Right now, what we're looking at primarily is what is the winning architecture for a hydrogen engine, because you really do want to take advantage of the stored energy in liquid hydrogen and also this tremendous potential heat sink that you have. So it'll be a very different thermal cycle. And recently, I think Graham mentioned it this morning, we've started an ARPA program in the US. So our approach to that will be define the winning architecture, pull the technologies you need to enable that architecture, and then build an engine around that. And then, of course, maybe it doesn't need to be said, virtually any engine, until we get to hydrogen, will be capable of running on 100% SAF.
Great. Chris, GE's perspective.
So when we think about the future, we have three pillars as well, very similar to what you've heard from my other two colleagues here. We start with advanced architectures. My colleague Gail this morning talked about the RISE open fan architecture, where we've committed to 20% better fuel burn than the current LEAP engine, which leads current technology today in operation. We think that's a very innovative and differentiated architecture. We're very excited about that. We're going to flight test that in the middle of the decade. Secondly, on electrification, we have a program with NASA and with Boeing specifically to demonstrate a 1 megawatt electric powertrain that we're going to flight test in the middle of the decade. And then finally, hydrogen, where we've committed, CFM has with Airbus, to do a flight demonstration of a hydrogen-powered engine in the middle of the decade as well. So 3 full-scale flight test demonstrations in the middle of this decade that we think make up the fundamental building blocks of the next generation technology, and the opportunities to not just look at those individually, but to combine those over time as they mature to really get a full capability of what we think technology can bring. And as my colleagues have said, certainly SAF, as we've heard about all day today, is a fundamental step for the whole industry to make sure we continue to put value in the existing assets that all of our customers have purchased.
Great. Thank you for that. So maybe on the airframer side, Rodrigo, do you want to kick us off to tell us what you're doing?
Yeah, I think on Embraer side, it's an interesting perspective because we have been working on this regional aviation for over 50 years, and that's where many of those technologies are expected to be introduced. So we are working with all of them. Last year, we concluded our work on the what we call the Energia family, which is a family of 4 concepts ranging from full electric with 90 seats up to a gas turbine to burn hydrogen on the 50 seats. And that was more on the technical side. On this year, the idea is actually that we interact with the market, with customers and airports to understand, go deeper in the technical requirements, and also to understand market potential, commercial conditions to actually make those concepts viable as soon as possible. So that's I think, what is cooking at Embraer for now.
Okay, thank you for that. Brian, how about Boeing?
Yeah, well, thanks for listening to me twice in one day, first of all, so I appreciate that. Sorry for you.
After you talked about SAF earlier, you can now tell us how you really...
I won't talk about SAF. I won't, and I'll try not to make you do math this time either, but no promise. All right, so with respect to alternative propulsion systems, advanced products, I like to think in terms of products, demonstrators, and technology. So from a product standpoint, one that we've announced so far with respect to advanced propulsion is the certification and pursuit of a battery electric product through our joint venture WISC. This is an urban air mobility application, battery electric, fully autonomous, that we're going through a process of building and ultimately certifying that airplane now. So that's in the product space. With respect to demonstrators, we actually have quite a lot of demonstrators. So we've mentioned, just mentioned the hybrid electric 1 megawatt demonstrator that we'll be doing with GE and NASA that we're very excited about. We also are pursuing the build of a full-scale prototype demonstrator of a transonic thrust brace wing. This will be traditionally powered initially, but we'll also have the ability to demonstrate many of the advanced propulsion technologies that were just spoken about here. And so that'll be a very large-scale demonstrator for us. With respect to hydrogen in the demonstration domain, we've flown 5 hydrogen or supplemental powered hydrogen aircraft to date. We've done a hydrogen fuel cell powered aircraft that was on a retrofitted general aviation aircraft. We've done a hydrogen combustion aircraft that was in a high altitude unpiloted system. We've done tests with respect to replacing commercial APUs with hydrogen fuel cell systems. And recently, we've actually done a ground test of what we think is probably the world's highest performing cryogenic hydrogen tank. And it's about a 16,000 US gallon tank. What we're doing right now is we're using all of that information along with a lot of the technology development, which I won't speak about just in the interest of time, in order to start to conceive what are those future potential demonstrators or future potential products that may start to fill in that space between, let's say, WISC at the low end and then Max 7 at the kind of high end. So we've been doing a lot of work to conceive of what those potential products and demonstrators are. We haven't announced anything to the world yet, so you'll see more in the future. But it's really all about synthesizing all of that information to understand what and when does a potential alternative powered aircraft start to make sense.
Great, thank you. Mark?
Yeah, well, it seems that things are coming in threes, so I'll go for the Airbus 3. So for our 3, so I guess the most visible one has been the 0E, which has been published. You've seen the 3 concepts, I'm sure, that have been put out there. And though in that area, we've recently announced the focus on the flight test for hydrogen burn. So obviously we're progressing down that road at some pace, with the actual intent to look for a product in service in the middle of the next decade. In addition to the hydrogen burn, you've also seen that we're looking at the tanks, we're looking at the fuel system, and we're also looking at the non-propulsive. So we've announced what we've named zero emission development centers in a couple of countries where we're focusing on some of those key technologies there. So that's one of the three on the hydrogen side. On the hybrid electric side, actually, this is a roadmap that spans quite a large part of our portfolio. And we see a large part starting actually in the helicopters domain. So here we see a real strong benefit, short-term benefit for going down the hybrid electric. A lot of learning we're doing in the helicopter domain that we're bringing then into the commercial aviation domain and bringing that through. So certainly we see that, and again, that blends itself to both SAF. It also blends itself to H2 burn. And then the third one, very similar to what we've seen before, is on the full electric, where this is a good sweet spot for the urban air mobility. So we have the City Airbus Gamma, which we're currently now proceeding down that road to produce that vehicle, and that's a full electric battery aircraft.
Great. Lots of activity in the industry, and no clear winner yet as we kind of look at technology. I think as we're thinking about decarbonizing by 2050, and as we're thinking about, when do we get these aircraft out there, we heard a few timelines from you, but what do you guys think will really be the time when we will see these aircraft or these new propulsion systems at least roll out and start, getting into service and being able to fly on them? Rodrigo, do you want to get us started on that question, given you guys have put some timelines out there?
Yeah, so from the technology perspective, right, we see that a hybrid could be actually being introduced just now, right, between, let's say, on the 2020s. And then we have a full electric could be introduced also relatively soon, depending on the size that we are talking, right? Then we have a little bit more challenge with fuel cell, depending on the size that you are talking. Then we are probably maybe 2030, 2035, and finally, when we talk about a gas turbine burning hydrogen from a technology standpoint, actually could be introduced earlier, but because we are, in that case, we are talking about typically longer range aircraft that needs more availability of hydrogen, probably we would be talking about a little bit later, 2035, 2040. So that's more or less how we see the introduction of the timing for the introduction of those aircraft.
I see General nodding in the group. Any other perspectives on timing from you, or do you feel that generally sounds like industry consensus?
Well, it takes a bit of divination and crystal ball reading, right? But there is a certain logic in maturing technologies, ensuring that we can fly safely, getting them certified, manufacturing them, and ultimately seeing them into service. So there is a certain logic, and definitely the steps we've just heard do make sense. I think it's important to underline the need perhaps to embrace new ways of working in parallel to the new technologies we're discussing. And Fly Zero, in this sense, has been a wonderful example for me of really agile ways of working applied to developing possibly a program, right? So very quick cycles, really new methodology, new collaboration across the whole segment and industry. So I think this will be just as important as maturing technologies to ensure we hit our targets in time.
The only thing I would add to that is when we think about getting all the way to product, we really need three streams to come together. The technology maturation that we all just talked about, the certification that Grazia just mentioned, and then the infrastructure that we've been talking about all day today. All three of those timelines are going to have to harmonize for us to really have it introduced for the flying public.
I think that's an interesting segue to another question, which is the question of infrastructure, right? And I mean, all of you have probably looked in lots of details and what will it take, whether it's on the electric side or on the hydrogen side, to make it happen. So as you kind of think about infrastructure, what is it that we need to put out there? Mark, do you want to kick us off on that?
So yeah, I mean, the infrastructure side is a significant question. It's going to have to be addressed and resolved. And I mean, we're really working with the specialists, the professionals, the industries in this area, whether it be companies like Air Liquide, whether it be operators like Airport de Paris or that. So we're working with those to look at all the different pathway segments because there are multiple pathways, okay? They all have their pros and cons. And we're really trying to figure out with them which are the best pathways, which are the most suitable for which different dimension and whichever avenue we should take. So we have these programs of work running with these partners, And we're really just exploring those at the moment to make sure that they align. But exactly as you've said, we do need these three dimensions to hit, and we're all driving with the same problem. We're all driving with the same sorts of technologies at the same time, which is, guess why we're all coming up with the same sort of timelines. So I guess the general consensus is a reasonably good one, and that is just another factor that we've got to get through.
Rodrigo, anything on infrastructure from your guys' perspective, given that you've looked at all the...
Yeah, I think one important element is the inertia, right, of the entire system, which is difficult to change. And in that perspective, I think starting perhaps from the smaller airports where it's easier to introduce infrastructure, either for electric or for hydrogen, for instance, I think that would be important. And one thing that we have to consider is that in many cases to reduce, in name of reducing carbon emissions, policymakers are actually trying to shift the short-range flight to rail, right? When you do that, you are actually disincentivize the smaller aircraft to introduce those technologies, and for smaller airports to introduce the infrastructure. So I think is something that we could think better on what are the ideal policies to actually reduce carbon emissions and allow the new technology to be introduced.
Chris, any thoughts on infrastructure to add to that?
So I think we have to maybe distinguish a little bit between the SAF infrastructure that we've been talking about, which is generally a supply challenge of generation, and the hydrogen infrastructure, which does not take advantage of the existing airport and other infrastructure associated with that. We're going to need both over time. How the industry, is going to allocate investments and how policy and incentives and mandates are going to set up, I think that remains to be seen. But there's certainly different technical challenges between the two, but an exciting time to pursue both.
I think you want to add something to infrastructure?
Definitely, this is where collaboration is more important than ever, and we're working together with EasyJet, for instance, at Rolls-Royce, to really understand infrastructure operation implications around hydrogen, around sustainable aviation fuel. But let's not forget, it's also about electrical flying, right? So really leveraging the fact that Rolls-Royce is a broad power-based company. We're joining forces between the divisions, Rolls-Royce Electrical, Rolls-Royce Power Systems, to develop also recharging infrastructure for eVTOL and commuter operations. So we need to tackle the full scope end-to-end.
Frank?
Yeah, I'd like to add to what Grazia just said, because we heard about SAF infrastructure, we're hearing about hydrogen as if they're separate. And there was a question in the last session, well, you have to pick one. I think actually if you pick one, you're liable to fail. If you think about what both need, long-term power to liquids, long-term hydrogen, they need electrical generation capacity. And so how do you convince the world to put all that generation capacity in if, when they're done, there's only a handful of aircraft to fuel on hydrogen? So I think really a winning strategy is use that electrical generation capacity as you build it for power to liquids, because you have a ready-made market today for that fuel. And then as you evolve hydrogen aircraft, you then start to convert that electrical generation capacity to making hydrogen. So I don't see the world building huge infrastructure for hydrogen unless there's an outlet for all of that electricity along the way. And then, power to liquid could be that outlet.
Great. So one thing I wanted to pick up on is, we had mentioned about decarbonizing and net zero and, sustainable flying, and all those things are slightly different. And I think the one really interesting thing about novel propulsion that it could go beyond decarbonization, so it could actually deal with some of those things of, not burning at high altitude, not creating NOx, etc. So how should we as an industry think about, climate impact more broadly, and then that in the context of novel propulsion? Brian, I know you've been thinking about that quite a bit. Do you want to get us started?
Yeah, sure. And I'll tie it with the last question on infrastructure too, maybe, is when I hear the phrase target true zero, I don't think CO2 only. And I think it's really important to think about two things: full life cycle impacts as one of them, and the other is non-CO2. And to me, that is what target true zero means. And I think that when the world sort of galvanized around this subject, I think we quickly gravitated to CO2. but I think that we have to have this more holistic perspective about full life cycle and non-CO2. And here's why those things matter, especially from an infrastructure standpoint. I think on infrastructure, it's easy to think about, I need this many megawatts delivered to airport, which will require substantial upgrades to the airports, by the way, depending on how much, how many megawatts you need delivered at over what time period. And likewise with hydrogen tanks and all the rest. The total performance of that from a life cycle standpoint and non-CO2 standpoint is entirely driven by what happens upstream of aviation. And that is to say, the world needs to realize that we have got to get to massive increases in renewable energy. If we don't do that, nothing that we do will actually solve the problem. In fact, if we actually just out on the ramp today had hydrogen airplanes, or in some cases large electric airplanes, depending on scaling and some technical things which we can get into, but hydrogen airplanes, if there was a hydrogen airplane sitting on the ramp to there, and instead of me flying back to America on the 777 that I flew in here on, or the 87 I fly back on, if I flew on that hydrogen airplane, I would dramatically increase my emissions, even over fossil Jet A, because of how we produce hydrogen today. And by the way, that's not picking on hydrogen. That's also the same for PTL. If I were to put PTL SAF in there, I would increase the amount of emissions. So all of this is to say our performance will be downstream of our ability to scale renewable electricity, and there will be dramatic competition for that renewable electricity from other sectors. It's not about getting to 100% renewables. It's about getting to 100,000% renewables compared to today's base, because we'll ultimately have to use that abundant excess renewables to produce green hydrogen, to produce PTL SAF. By the way, we don't have a choice. I told you I wasn't going to make you do math, but we don't have a choice because of the math I did on the last panel. We don't have a choice. That question said, can you do this or that one? You have to do them both. We did the math. We'll be downstream of our ability to transform the renewable electric grid. And we have to be clear about that as an industry, is we can't just say, we're going to show up with this technology and it's going to work. If that doesn't happen, that technology won't actually improve the environment.
Very, very, very good point. And Chris, anything you would say from how do we think about total climate impact and kind of the energy challenge that Brian points out?
So I think in terms of emissions, as an industry, we've always had a strong focus on fuel burn as an economic driver for the industry, and that's really been commensurate with CO2 reduction. I think now that we're broadening the discussion to talk about NOx, noise, contrails, other kinds of environmental factors, it is a much richer discussion. And we've historically just used the regulations to get there. I think we're now getting to the point where we can get past that. The GE9X engine that we certified about a year or so ago is 55% below the regulation in terms of NOx emissions. And I think that's a trend that we're seeing in a number of companies to say it's not enough to just meet the regulation. We want to find ways to keep getting better. And I think that's a healthy discussion for us to have, as how we balance all those factors as we continue to make the industry more environmentally friendly.
Mark, go ahead.
And just to pick up, so on the, let's say on the emissions side, the non-CO2 effects, these have the biggest error bars, right? In all of the, so I kind of look at the problem in terms of that there's a science part and there's an engineering part. So the engineering part, fine, that's more on the aircraft, but the science part, there's still some work to do there. And these error bars are still quite big, and we need to get a much better understanding. So that's what we're trying to do with a lot of the test flights. You see a lot of the test flights on 100% SAF. We've got chaser aircraft going behind, trying to measure, because the atmospherics at high altitude are considerably different. So we really need to get a much better understanding to see what that impact is for both SAF, the different forms of SAF, and also for hydrogen as well. So that's one of the key drivers, to make sure that we've got that knowledge. We can feed the scientists with more data. They can help us understand what those impacts are, and then we can do the engineering to find solutions.
By the way, if I could just agree with, I totally agree. There's actually an urgent need to do this scientific research, because if you think about how long it takes to conceive of an experiment, execute a flight test, discover the insights, work to actually reduce those error bars over time, that's a years-long process. Now you're talking about launching potential strategies, incentives, products, et cetera, into the face of that, and you back up right to left. That implies that it's actually of urgent need for us to start doing that non-CO2 research. And just to plug Rob Miller's work at the Whittle Lab, I think Rob's models and the team at the Whittle Lab are exposing a lot of the uncertainty and the value of, boy, I wish that was actually a lot smaller. It's not about what's the answer, it's about making it more precise.
Yep. For those who are not familiar with Rob's work, they will be publishing a report under the TTZ banner in the coming weeks, so stay tuned for that. Sorry, do you want to?
Just a quick comment. I think it's, as said, right, it's very important to understand the full implications, the full effects on the climate of the different alternatives, so we don't make bad decisions, right? And there will be a lot of money involved in those decisions, so that's very important. And this is when we talk about within aviation, but it's also important when we talk about aviation versus other modes of transportation, right? We have to compare those things and take decisions on what's the most sustainable way of transport, considering the entire cycle, right? The true zero emissions, all the effects, right? And this is, I believe, it's important also when discussing the different alternatives.
That's it, Frank. Anything you want to add to the total climate impact question?
Well, much has been said, but indeed, I have the impression the societal amygdalas have been hijacked around the CO2 topic, right? And we'd be remiss if we didn't broaden the horizons to capture other anthropomorphic emissions, regardless whether regulated or not, right? And so indeed, there is an engineering challenge in continuing to develop our products to indeed be mindful not only of CO2 emissions, but also NOx, such as instance, continuing to improve lean burn combustion systems for ideal pre-mixing of fuel and air before ignition to then enable really full combustion of fuel with reduced NOx, reduced non-particulate matter emission, and as a consequence, also a beneficial impact on condensation trails. The scientific aspect of it is fundamental. There still is a lot of research to be done. And it's also important that with each trial we do, each flight, each sustainable aviation fuel, 100% SAF trial, that we really focus on tilting the scale and focusing on understanding fully what the impact is of SAF on our engines, on our technologies, and also continuing to investigate potential other pathways, even more environmentally sustainable than the current ones.
But just say a couple of things, just reinforce what everyone has said. Internally, we do look at the entire climate impact as individual companies, but we don't communicate externally. We have a lot of discussion about CO2. I do think we run the risk of public perception of why didn't you tell us about NOx and contrails? And so I think we need to start talking about everything, not just that. And on the subject of contrails, we heard we need a lot more climate science on that. I agree completely. But on the other hand, technologies exist. You know, Raytheon has many technologies that could be deployed to avoid contrails. So if we could fully understand the climate science around it, it may be fairly straightforward to avoid it. And that would be a big, big win for the industry.
Great. Thank you for that. I want to go back to some of the technologies you listed in your introductions, and particularly hybrid technologies, right? Because I think I can get my head easily around, you know, what we can do with hydrogen, what we can do with battery electric. Hybrid always feels to me like a step, but maybe it's not. Maybe it is something more than that. So I know you've looked into hybrid at length. Frank, do you want to get us kicked off on, tell us about hybrid. Is it a long-term solution? Is it a stepping stone? What is it?
It's both. It's a step and it's long-term, especially if you move towards hydrogen. So today, hybrid in a regional could be a 50% hybrid, and as Graham showed earlier, could be up to a 30% reduction in energy required for a regional turboprop mission. So that's a big deal. In a narrow body type application with today's technology of energy storage and batteries, maybe it would only be 5%, but that 5% could be used for electric taxi, so you don't turn the gas turbine on until you're ready. It could be used to downsize the gas turbine. Gas turbines are sized for events that rarely happen, like an engine out on takeoff, or a blade out, or some very remote activity. So you could use the electrical capacity to help with that, so you'd have a more efficient engine. Long term, though, as I said before, with hydrogen, you're going to have a lot of stored energy, and a lot of that energy could be used to make electricity. So if you've already developed the electrification technologies, all of a sudden you're going to have a very ready source for electricity. Phase change, turboelectric, be a small unit providing lots of electricity, and so that's why I say it's a step today, but it's also an architecture for long term.
Great. Rodrigo, I know you guys have a hybrid model in the pipeline. Tell us a bit about your views on hybrid.
Yeah, so I agree. It's a short-term and a long-term solution. On the short-term for regional aircraft, it's a possibility. We could introduce that from a technology standpoint earlier, and we are actually doing the studies to see if we are able to close the business case and make that type of concept available in the market as soon as possible. It's also a way to learn more about electrification, right? To get more understanding, to use that type of solution in the field, which is something important. So I agree. I think it's very relevant for now, and also for understanding potential future solutions.
Chris, hybrid solutions, how do you think about it?
So I think it's exciting the same way that we've seen the automotive industry go ahead of us, right? And if you've ever driven in like a Prius or something like that, and you can see how it goes between the gas turbine and the battery and all the different things, it, exactly as Frank has said, it really takes you away from the traditional constraints that we've had, right? That have largely been mechanical based, hydraulics, pneumatics, and really be able to move and use electric as a variable that we haven't been able to use really in the past. And so that gives us a lot more flexibility both now in terms of how we augment a gas turbine, and also leads us down the path of how we can scale more electric over time, so that we have a pathway to the future as well.
Brian?
It's complicated.
Tell us.
So, I think hybrid, the way that I like to think about the energy transition, advanced propulsion, and so on, is I like to think about efficiency technologies and then energy transition, where energy transition is things like drop-in SAF or even hydrogen as an example. Hybrid is kind of an efficiency technology for the reasons that were just stated. So at the large end of the scale, maybe less than 5% fully integrated efficiency benefit. So there is an efficiency carrot there, which the amount of which kind of remains to be seen when we really think about how to fully integrate into the airframe and make sure all the voltages are aligned and all these deep technical things. What's the overall integrated benefit? It's going to fit into that efficiency category rather than the energy transition category. Now, the reason that I say it's complicated is because at the high end of the market, we could think about this kind of simply in the efficiency technology, kind of what I just described. At the low end of the market, there are a lot of potential uses of hybrid, and the benefits or penalties depend on how it's operated. So just as an example, small electric airplanes, you can use a serial hybrid system where you have electric motors essentially as the prime movers. Those can enable new capabilities, so vertical lift, short takeoff and landing, range extenders for purely battery electric and then extended range. Now, the benefits or penalties of all of that depend entirely on how it's operated and essentially against a substitute, which is what makes it so hard. So the question isn't, I can operate, on a battery for this far and then on hybrid electric or on a, SAF or something for this far. And so I have X much benefit versus, a 1990s airplane. It's really how much benefit do you have against an equivalent technology substitute to do the same thing. In some operations, that can make a ton of sense. In other operations, it actually has penalties. And so that's why I say it's a little bit complicated depending on where and how used.
Grazia?
I couldn't agree more, Brian. It's complicated to continue developing concurrently and coherently so many different technology pathways. But there's really a lot of sense in certain applications in certain markets and segments, right? So fully electrical propulsion is just around the corner. Entry into service is imminent. Systems are relatively simple. Technologies are mature. When we start extending the range, we know what the limiting factor is. It's the energy density of batteries, and that's where hybridization does play a significant role. Perhaps starting with piston engine, parallel hybrid type of simple solutions, then going into turbo generators as we go on larger platforms as range extender. So there's really a bouquet of, or buffet, open buffet, really, we can pick out from to make sure we have the best solution for the best segment and range.
Mark, anything to add on hybrid?
Well, a lot's already been said. So you're right, Brian, with the efficiency angle. Yep, okay. You know, that's something. The integrated efficiency. I fully agree with you there. So that's fine. You know, we want to cache that. It's then what does it unlock? Okay, and it's complicated is a good way of expressing it. You know, as the storage technology becomes more and more capable, that also helps you unlock more and more features. So we actually have a sort of a menu of features that we think we can actually start to unlock over the years, as not just the hybrid technology on the engines improves, but how we could then store that, how we can integrate that, how we can start to replace other systems and get those benefits. Not all systems show benefits. So, you know, if you're trying to say, oh, you know, I want to completely remove hydraulics, you might start to end up with some pieces which you go, actually, this piece here is really difficult. Do you actually want to go to that extreme length in order to do that? So, but it does give you a lot more options. And that's one of the fundamental things that it really does unlock for us. So it's a real good direction to go, not just for the propulsive efficiency, but for all of those additional things that it unlocks, but they're complicated.
Interesting. So since we're starting to kind of get into some of the technology complications here, would just love to ask you, I think all technologists at heart, what are the big technology changes ahead of us? I mean, we have a timeline, we have a plan, but what are the big technology pieces we still have to overcome and develop? Do you want to kick us off, Chris?
So I think we've talked a lot about them today. I think in terms of the infrastructure, certainly one of the technology challenges and how we get that to work, particularly for hydrogen. I think the challenges around being able to certify and make sure these novel technologies are safe and reliable, getting past the public perception, because some of these airplanes and engines may look different than what people are used to. But I think the fundamental science is sound, and many of these are not just invented now. If I look back to our open fan program, for example, for CFM, we flew our first open rotor engine back in the late 1980s. And at the time, the world really wasn't interested in fuel burn reduction of that magnitude because of economic factors. But we've been developing that over the last really 4 decades, and we've had the GE90 first composite fan blade. We're now on our 4th generation for the GE9X fan blade, and that's about the same diameter as the 4-meter diameter open fan that we're talking about for RISE. So these technologies that may seem quite novel and quite revolutionary often have something we've been working on for many, many years and are just finding the right application now. So I'm encouraged by the challenges that we feel like we've got a track record to support.
Great. Rodrigo, what are your thoughts on the technology challenges?
Yeah, I think as said before, perhaps the main one is on how to really produce sources of fuel, of energy in a really clean way, right? In a really green way and effective way. I think that's perhaps the most basic challenge that we have. On the aircraft level, then we have, several challenges. That is on the electric propulsion, for instance, the energy density, of course, it's one big challenge on when you talk about fuel cells. There is the thermal management challenge as well. When we go to hydrogen, there is the tank, the storage of the hydrogen, which is another big challenge. And when you mix things like hybrid, for instance, then you have the challenge of control and integrate things. So I think those are the main technologies that I think we'll be working on the next years.
Mark, from your perspective?
I think a lot of the technologies, let's take on the aircraft, a lot of the technologies are known maybe from other industries. Some of the key challenges is then bringing them to the aviation industry, and that's some of the big challenges that we see. So you see, and some of the technologies, other industries are putting them slightly in a different direction. So it's really say, okay, that's fine. You're maybe going for a different energy density than aviation would prefer. So how do we bring that back? Have we got enough market capability in order to do that and bring that investment in these other sectors to there? If you look, yes, with the hydrogen, you've got the whole thing with the tank manufacturing, keeping things at cryogenic levels, priming, and state change. State change is something is going to be new that we'll have to manage. So there are some new technologies in there, but what's good is having a space industry. So we can pull very heavily on the space industry. They've got years and years of experience. So it's really going to those other industries and really seeing how we can adapt those technologies to the problem that we've got.
Grazia, I can tell you have some thoughts on the question of technology challenges.
Well, yes, we have no chance of getting bored on the subject. There's many challenges on each of the streams we've just been discussing today. So definitely on the gas turbine continuous improvement and efficiency improvement field, continuing to develop advanced low-emission combustion systems. This is something we're very much engaged on our UltraFan demonstrator in Derby. And when it comes to hydrogen, well, that's a totally different game. So, right, the combustion of it will be a challenge. Just imagine having to convey a delta T from 20 Kelvin to 300 Kelvin, right? So flame behavior, water vapor generation, these are definitely some of the parameters we're going to have to be able to control. In addition to the equipment, right? Going along with it, pumps, heat exchangers. There's a lot out there coming from other industries, either space or stationary use. We ourselves have a reciprocating engine running on hydrogen being tested currently in Magdeburg. But taking things to the sky does present different challenges. So we won't be short of activities.
Frank?
Yeah, one thing I'd add, we all have very, very smart people that are solving individual technical problems, and we're pretty good at solving our internal technology development issues. I think the next big challenge is propulsion system aircraft integration, because there's a lot that can be done to improve the overall efficiency. So right now I'll simplify, and it's like, okay, Boeing, Airbus, we have a new airplane and we left a spot for you to bolt an engine on. It's more complicated than that, but basically we manage everything through interface documents. I need this much air, I'm going to provide this much fuel. In the future though, as you move towards electrification, and certainly if you move towards hydrogen, the idea that you're going to do these separately and not optimize around a system, it's a very difficult concept for me to grasp. We really need to be working at a much closer level, because the power and the thermal management now will be integral between the airframe and the propulsion system. So I think that will be a challenge, because we're going to learn, we need to learn how to work more closely together on those kinds of activities.
Brian?
Well, challenges are opportunities for engineers. So I'll talk about opportunities. I mean, I really think that this is kind of a once in a multi-generation renaissance of problems to go solve. So from an engineering standpoint, it's really every engineering type, honestly. And this is what I tell folks, when we're off talking about who do we need to create a battery, to create a battery that can be certified. You need chemists, you need material scientists, you need electrical engineers, all things you would think. You need a lot of software people too, which is not really thought of all that much. If you're talking about products that are, let's say, much smaller products, 20, 50 seat airplanes, we're going to have many more of them as an example. If we'll have kind of smaller scale products that are serving the market today, we'll have many more of them. Those probably need to be more automated. And we also probably need to think about how do we produce them using processes from other industries like automotive, you're mentioning. So it's all these kind of, once you peel back the layer, 1 or 2 layers on some of the trends that we're talking about, there are all these deep and interesting engineering problems to go solve and to think about that are not obvious at first blush, but then you think, gosh, I'm going to make many hydrogen airplanes, and now I need to think about how to produce them like in the same way that I produce cars, because I need many more of them, or whatever the situation is. So that's really what's happening behind the scenes that's so exciting right now for engineers. It's kind of a renaissance from that standpoint. I completely second the point on propulsion airframe integration. I think what you see is a lot of engine manufacturers thinking about airplanes, a lot of airplane manufacturers thinking about engines and propulsion systems. These are obviously, blending, and I think as we all work through the product strategies in the face of uncertainty here, it's there's just unbelievable opportunities.
Yeah, so maybe building on that, I mean, there's an interesting question around how important are new airframe designs going to be to take real advantage of this, right? So to, optimize them for hydrogen storage or even for distributed electric propulsion or so, versus how much can we rely on our old kind of designs that we know well and know how to produce cheaply. So kind of as you think about this challenge of new airframe versus, maybe even radical new airframe versus traditional airframe, how do you think about the trade-off there? Maybe you want to kick us off, Mark?
So there's always been a constant drive for more efficient airframes and improved manufacturing, and that. So different parts of the airframe have different requirements on it, and that drives a lot of the technologies in there. So if we take the wing, for example, we're still driving for a huge amount of efficiency improvement through the wings. And we need to do that, not only because we want to reduce fuel burn, we want to reduce cost, but we'll have additional drag in other areas because we know if we're going to put tanks in the fuselage is going to be longer or fatter or whatever, so we're going to have additional drag elsewhere, so we've got to compensate. So there will be differences in the airframe. So the sort of the historic traditional work of airframe improvement, materials improvement, lighter, stronger, this all continues and has completely applicable future to complement all of the other technologies that we talk about. So it's really important that we continue with all of those. In terms of the configuration of the aircraft, it really depends. We always draw the things like the flying wing. They come with different challenges, but they don't necessarily come with aerodynamic or propulsion. They come with even more practical challenges that we have to address. So I think the airframes could still look maybe quite traditional, because it's a well-proven recipe and solution. So that's kind of where I think, and I see all the Fly Zero, they still look quite traditional, don't they? But they come out at the end of the day. I've seen all sorts of campaigns, and at the end of the day, when you see all the down selections, you go, okay, you come back to the same answer again. So, so you see all of that, but it doesn't mean that the airframe is forgotten. It is progressing at some pace itself.
Rodrigo, on the airframe question.
Yeah, I see a little bit of the same thing. And from when I talk to the engineers in our defense design, they tell a lot that this is the best time to be an engineer. Like, you have all the freedom, let's say, to rethink everything, right? When you are talking about incremental improvements, right, then you are really tied to existing constraints, right? All kinds of. Nowadays, you have to rethink everything, right? So I think it's I don't see people actually constraining because of existing infrastructure or existing know-how. Actually, we are trying to design, let's say, the best, the most efficient way. But what happens in many cases that we see very crazy designs in the beginning, and at the end we close to very traditional concepts. But I think it's time to rethink, right? To have give a chance to novel designs.
Chris?
I think this point on talent is a really, and Brian mentioned it as well, that, you know, I think every single one of us is hiring about as many engineers as we possibly can right now. And, you know, we're at a point in the industry where I think for the last several years, a lot of the attention has gone to the space part of aerospace, the SpaceX, Blue Origin, and so forth, and they've had terrific accomplishments. But we really need a new generation of young people who are excited about the future of sustainable aviation and all these technologies we're talking about, all the different disciplines that Brian mentioned that we're going to need. And I think they will bring a different view of some of these and a more willingness to challenge the status quo in terms of how we think about all of our design concepts going forward. So I would make a plea for more broadly if we need more engineers, so we have to attract more young people into the industry to help us all out.
Thanks for that. Brian, any thoughts on the airframe design and what we might need for novel propulsion?
My favorite airplane is the Boeing 367-80, and it was a prototype airplane that proved out the the potential of commercial turbojet-based tube and wing architecture. And I love that, both because of the business bet that represented. So someone had a perspective on the technology. This technology is going to work, and we're going to bet the company to go off and make a prototype and show that this works. And then the industry since then has rallied around that platform, that tube and wing platform, and we've been on a I think 80% decrease in the energy per seat mile since the introduction of that technology. Now, what's interesting is how far can you press on the efficiency of that architecture? And I think basically where the industry's been for the last many generations of product is 15 to 20% per generation of product. A lot of which comes from new engines, and a lot of which comes from airframe aerodynamic updates and all these kinds of things. How much is left? And so one of the things that we have said is that we're very seriously studying a change in that architecture for a next generation product. And so we've been looking at the the transonic thrust brace wing as a change in that architecture that allows for a more aerodynamic airframe, but also more underwing capacity and some other things that are very interesting. We've likewise studied things like the blended wing body, and we've done a lot of studies with NASA on these subjects. No decisions have been made on that point, obviously, but I'll say if you step back from some of the energy transition subjects and you think in that efficiency stream and you think, how do I get my next 20% and the 20% after that? That's where you start thinking about these new architectures. And I think there's incredibly exciting potential to go off and demonstrate that and learn what those new airframe architectures really mean.
That's it.
Well, I think it turns out that the Wright brothers and sister, let's not forget Catherine, did come up with a pretty robust concept, right? Apart from the fact that the flyer looks like it's flying the other way around, it's a fuselage with an empennage and wing, right? So it's a great concept, and sure is, by opening the door to new technologies, more and more electrification, and of course hydrogen, we do also open the door to new radically new configurations. And the fact that we're harnessing on technologies which are not exclusive to our industry and importing talent from adjacent industries definitely increases the chances also of new configurations perhaps being coming up. So definitely the door is open.
Anything you would add to that, Frank?
Well, I say if you look, we heard earlier today, I think 80% reduction in emissions since the dawn of the jet age, and I think about 70% of that is since 1990. Largely, not exclusively, but largely come from propulsion, and I think maybe there's an economic basis behind there. So if a propulsion company wants to try something new, they're not betting necessarily the future of the company, whereas an airframer, as Brian just said, very well might be. So the idea that you're going to go forward with a blended wing body, I think some of those programs really do require some public-private demonstrations. They'll be very expensive. Of course, you'll learn a lot. And at the end, you would know, yeah, this is a huge advantage and we should move forward and now bet our company on it. But there seems to have been over the last maybe 20 years, not as much enthusiasm to do those big kind of projects with something really radically different. Maybe the truss brace wing will partly go forward with that, but it would be nice to see a full-size blended body wing and to know once and for all what are the benefits of that kind of an architecture.
I'm going to pick up a question from the audience here, which is around the challenges of certifying, both novel propulsion and the whole system that goes with that. So how easy will it be for us to get a hydrogen aircraft or a hybrid aircraft or a battery electric aircraft truly certified, for transport scale aircraft? What are some of the perspectives you guys have? Mark, do you want to kick it off?
So we know what's required in terms of the overall objective, so that's not changing. So we know where we've got to get to. Yes, it does require a lot of discussion, debate, and collaboration with the authorities to understand what the different challenges are, what are the differences, the deltas from what we know today to what's coming in the new, and to figure out what the different risks are, how we're going to manage those, what are the different options, how do we look at those risks, do we take them from this perspective or this perspective, how do we manage that, how do we mitigate that. So this is an ongoing dialogue and an ongoing exchange, and then it has to be backed up with evidence, experimentation, and proof. So I think the general approach and process is a well-trodden path. Yeah, I don't think there's anything new in that. Yes, the technologies are new. Yes, the discussions are maybe slightly different and the debate is slightly different. But how we go there and how we get there is a well-trodden and well-proven path.
Yeah, maybe I'll just introduce two terms that I think a lot about on this subject, both for autonomous systems and for alternative propulsion systems and so on, is equivalent level of safety is the first one. That's the regulatory threshold that sort of sets out, we know what the certification basis is today, and everything will be judged through a lens of at least an equivalent level of safety. And so that's the first topic. And the second topic is once a certification basis is established for an autonomous system or a battery electric system or future hydrogen systems or so on, once that certification basis is established, the real hard work is in the alternative means of compliance with that certification basis. And so that is to say, it's easier to describe for an autonomous system, that may say the pilot shall do X. Well, if you don't have a pilot on board, then something else shall do X. And so there's a long dialogue that goes on with respect to making sure that however that function is being provided ultimately to the system is equivalently safe rather, and can be validated as such. And so, as Mark points out, that is a well-worn path, but the discussions depend deeply on the technology that's involved.
Great.
Let's not forget that even for sustainable aviation fuels, which were not part of your questions, well, we're still not quite there, right? We will be demonstrating full compatibility of our products by 2023 with 100% sustainable aviation fuel use, but we're not there yet with the certification and also the certification of pathways related to SAF. So easier said than done sometimes.
Other thoughts on certification? Chris?
So I'm optimistic that two of our largest regulators in the FAA and EASA have been great advocates for sustainability in addition to being strong stewards of safety. And so they've certainly, you look at EASA focus on environmental labeling here in Europe. You look at what the FAA has been doing with the CLEAN program and so forth. They want to help us find a solution. So I see the regulators as partners in this. We all want to agree upon the rules. We don't compete on safety. We agree on what the rules are, and then the best design wins. And I think bodes well for the future in terms of certification.
It's very, very encouraging to hear. We're almost out of time, but I want to ask one last question. So we'll have to keep it brief. But as you think about what are some of the misconceptions out there around novel propulsion that you'd love to clear up, given that we have a attentive audience, what are some of the things that either drive you crazy when you read it in the media, or you think you just want to shed some light on? Brian, I could tell you.
I knew you were going to come to me. Okay, the thing that I to use the framing of your question is that these are an or rather than an and so not to redo my math from the sustainable fuels panel, but really that's how we think about it, which is this is an and And so, you know, we know that we've got to scale sustainable fuels under any circumstance of the uptake and the success of these potential future advanced technologies. We know we've got a somewhere between 800 and 1,000 exit. And so I think then it's a question of and do what, and so and on what timeline. And so those are the things that that will get worked out over time here. But it's not an or, it's an and. That's the most important thing I'd leave people with.
I couldn't agree more. I mean, we've had enough of seeing hydrogen played against sustainable aviation fuels, very often forgetting that hydrogen happens to be a constituent of SAF. And therefore, when we get there with the technologies, the maturity, the safety, it will be cheaper to fly on hydrogen than it will be to fly on SAF, most likely. And for hydrogen, we can count on cross-industry effects to ramp up and scale production of green hydrogen. And when we talk about hydrogen, often I still hear, oh my gosh, the Hindenburg as first reaction. Well, yes, let's not forget that tanks at that time were made out of cotton. I can assure you technology has progressed and we're looking into safer solutions.
Well, that's good to hear.
It'd be weight efficient, though.
Other misconceptions, Frank?
I'll preface it by saying virtually everything I read drives me at least a little bit crazy. What bothers me most is not necessarily the technology, but the investment that the industry has made in technology. Sometimes you read there's a perception that the industry has not done much up until now to improve emissions and improve efficiency. You know, nothing could be farther from the truth. And, you know, we've spent literally billions and tens of billions of dollars over the years to improve efficiency, develop low emissions combustion. And so when we now say, hey, we've been on this path and we're going to go further, I'm not sure I read acceptance of that. Sometimes it's we're not portrayed as an industry that has done everything that we actually have done.
I think that's exactly right. I mean, if you look at a literally 100-year track record of innovation with an underlying focus on safety, resilience through incredible economic cycles over that time, and now, as Grazia said, flying is more available and affordable than it's ever been in its history. Bringing people closer together and making the world a smaller place, if there's any industry you'd want to bet on, aviation would be the one to bet on.
Great. Well, look, thank you so much. We're unfortunately out of time, but thank you so much for making that. It was a pleasure hearing your perspectives on the topic of novel propulsion. And yeah, I think we'll hear from some of the new entrants after the break. Thank you, everyone.
Thank you.